All right, so bonding 3, this is just like a little add-on. So we did ionic bonding for bonding 1. Bonding 2, we started to look at covalent bonding and the shapes, the geometry. Now we're going to start looking at the nomenclature, or looking at it again, and looking at coordinate covalent bonds and network solids. All right, so don't forget to do your Travelog 5.3. So molecular nomenclature. Charges 1 plus versus 1 plus. An ionic compound, there is a transfer of electrons. Remember, that's a take, resulting in ions with full charges. In molecular structures, sometimes the electrons are not shared evenly, resulting in partial charges. So looking at this, like HCl, that's the ionic, and then you got H2O, which is covalent. Because of electronegativity differences, the bonding electrons are not shared evenly. So if you were to take this and subtract, like 3.5 minus 2.7, there's going to be a difference between the two. And the more electronegative an element has, the greater possession of the shared electrons and will carry a partial negative charge in the structure. So looking at this, like the hydrogen and chlorine, sorry, that's not an ionic, it is a covalent. Because it is more negative, like there's more over on the chlorine side, it's gonna be more negative towards that. It's gonna pull towards that. Just like with the oxygen. You got the little tiny hydrogens that are just a little bit positive, but the oxygen's gonna it's gonna want to pull it more towards itself. Remember, it's not taking, doesn't have enough electronegativity to take, it's pulling it towards itself. So in the formula, the positive part is generally written first and the negative is second, with the exceptions of CH4 and NH3. Carbon and nitrogen are more electronegative than hydrogen and will carry the negative oxidation state. And those are the only exceptions, CH4 and NH3. So method 1, the stock system. We looked at this. Since most nonmetals carry more than one positive oxidation state, remember those are the transition metals, a Roman numeral will be needed on the positive element. The stock system may not suffice with formulas like NO2 and N2O4. Though they are completely different molecules, nitrogen carries a +4 in both of them. So you have the traditional system, which is a series of prefixes that are commonly used to name moleculars. The prefix indicates the subscript numbers, not the oxidation states. So remember that. These are the subscripts, not the oxidations. Looking at this, you got the 1 through 10, mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. So looking back at those, what would have been stock of nitrogen 4 oxygen, nitrogen 4 oxygen, and would not work out really well, we're going to use the traditional system. So we're looking at the first, and looking at this, there's only one nitrogen, so you just say nitrogen. 2 oxygens, dioxide. And remember, it ends with "ide." And then looking at this one, you've got N2, so it's dinitrogen. 4 is tetraoxide. Note the mono is optional on the first element, but not on the second. So you could say mono nitrogen dioxide, but that's just a mouthful. You don't have to add that mono on there. But if you look at the second one, here's my example for the second one. You have CO. It's carbon monoxide. Again, you could say monocarbon monoxide, but it's easier just to say carbon monoxide because you know there's already one there. Okay, so real quick, you're gonna finish up the nomenclature in the homework in the green pages, and we're gonna look at some covalent bonding, coordinate covalent bonding. So this forms between two nonmetals. A pair of shared electrons is supplied, donated by a single atom. Common ions containing a coordinate covalent bond, ammonium and hydronium. So looking at this, you have H2O and HCl. So water and hydrochloric acid. This forms hydronium. That's 3 hydrogens. So it's OH3 and chlorine. So this is a coordinate covalent bond. NH4Cl, ammonium chloride. So remember again, this would be the coordinate covalent bond right there, the polyatomic ion. Oh, sorry, this is what is the coordinate covalent, sorry. So a positive charge, we're looking at this, we've got a lone pair, NH3 has a lone pair, and then you've got HCl. And when you combine them together, the hydrogen on the chlorine pops off and it connects to the nitrogen, making it NH4, and I lost ammonium ion. So the positive charge, because only the hydrogen nucleus has moved to the nitrogen. So this has more electronegativity than the chlorine. So it literally pulls that hydrogen off it. They separate, and it forms this coordinate covalent bond. All right. So what is a network solid? This is bonding is covalent. And it's unusual because of the hardness and the extreme high melting points. Because remember, ionics have those high melting points. They usually have the lattice structure. But looking at these network solids, they're covalent. They're not ionic. So some examples. You've got silicon carbide. And looking at this, you have the carbon face and you have the silicon face. And this forms a network solid, along with silicon dioxide, like quartz or sand. That is also a covalent bond, but it's a network solid. It's a solid. It's got like a lattice type shape to it. And then my favorite element, carbon and graphite and diamond. This is just carbon all together, right? It's a covalent bond, but because it has its structure, it networks solid. It can form so many different things, from the lead in the pencil that you use to the diamonds, like on my ring. Oh, I love carbon. Carbon's everywhere. But again, you can see that they're both made up of carbon. It's all carbon, but because it's a network solid, the way it's put together, I believe it's like it's called graphene shape. It becomes a network solid. So cool. So don't forget to do the Travelog 5.3. I know it was really, really quick. Hand that in. You have the study guide. Make sure to do the study guide because we're going to have a quiz pretty soon. If you have any questions, please don't hesitate to ask. Hope you guys have a great day.